You've seen the symbol, you definitely know the name, the transformer. But you know what? That simple little diagram from your physics textbook is hiding a really fascinating and kind of messy reality. So in this explainer, we're going to peel back the layers and uncover the real story of how these essential devices actually work.
Yeah, we all start with this symbol, right? Two coils, a core, and this promise of a perfect, magical energy transfer. But I'm here to tell you, in the real world, that perfect picture is, well, it's basically a myth. It's time to look inside the box and see the beautiful complexity that engineers are actually grappling with every single day.
So to really understand reality, first we have to start with the myth itself. Let's just quickly revisit that perfect or ideal transformer, the one that only exists in the pristine world of a physics textbook.
Okay, so in this perfect little world, every single bit of magnetic energy, what we call flux, from the first coil, just magically and instantly links up with the second coil. The core has what's called infinite permeability, which is really just a fancy way of saying it costs zero energy to get that magnetic field going. It's a perfect, lossless system. But of course, the real world is never quite that tidy.
And that untidiness, well, that brings us to reality. Real transformers have these unavoidable imperfections that engineers have a great name for, parasitics. These are the real-world physical effects that just get in the way of our perfect model.
So here's our first dose of reality. A real magnetic core isn't magic. It doesn't have that infinite permeability we talked about. This means you actually have to spend energy just to wake up the magnetic field inside the core. We call this magnetizing inductance, and you can almost think of it like an energy tax you have to pay before the transformer can even start doing its main job.
And then there's the second imperfection, leakage. In the real world, not all of the magnetic field from that first coil actually makes it to the second one. Some of it just leaks out into the space around it. This leaked field stores energy too, and we have to account for it with something called leakage inductance. It's just another step away from our perfect lossless stream.
So faced with all these messy parasitic effects, how do engineers actually get any work done? Well, they build models. But here's the twist. There isn't just one correct model. The right one to use depends entirely on the problem you're trying to solve.
We basically have two main approaches here. The physical model tries to represent what's actually physically happening on the inside. Every component in this model maps to a real place where energy is being stored. The mathematical model, on the other hand, it's all about the outside. It doesn't really care why the transformer behaves the way it does, as long as it accurately predicts the what, the relationship between voltage and current that we can measure.
And this is such a crucial point. Sometimes, for purely practical reasons, you deliberately throw out the physical truth. Maybe you don't even know the exact internal construction, or you just need a simpler circuit for your analysis. In those cases, you create a mathematical model that gives you the right answers at the terminals, even if its internal parts are just convenient fictions.
Now this is where things get really, really interesting. We've been talking about simple two-winding transformers, but the complexity just ramps up exponentially when we add a third or a fourth winding to that same magnetic core.
And to put it mildly, things get complicated fast. Every new winding creates magnetic links not just with the first one, but with every other winding in there. You end up with this tangled web of magnetic connections, and to model it accurately, the number of parameters you have to track just explodes.
I mean, check this out. The growth is staggering. A standard two-winding transformer needs 3 independent parameters to be fully modeled. Add just one more winding, and that number doubles to 6. A fourth winding? Now you're at 10 parameters. As you can see, the relationship isn't linear at all. It grows way, way faster than the number of windings.
But all this complexity also unlocks some incredibly powerful new designs. By arranging the magnetic paths in different ways, engineers can create specialized tools. For instance, a series wound structure forces all the windings to share a single path. This is absolutely perfect for scaling voltage, creating multiple outputs that are precise ratios of the input. And its elegant dual, the parallel wound structure, does the opposite. It's designed to make the currents in each winding scale together. So you have 2 different structures for 2 very different jobs.
So, okay, we have physical models that explain the why, mathematical models that predict the what, and all these increasingly complex structures. This brings every single engineer to a critical dilemma. Which model do you choose? And the simple answer is, there is no single correct model. The best model is the one that's most useful for your specific task. If you're an engineer designing the transformer itself from scratch, You absolutely need the physical model to understand exactly where all that energy is being stored. But if you're a circuit designer just using that transformer as a kind of black box, all you care about is the mathematical model that accurately predicts its behavior.
Honestly, here's the perfect analogy. The physical model is like the anatomical blueprint of a horse. It tells you how it works, and it's essential if you're a veterinarian trying to fix it. The mathematical model? That's just the horse's top speed. It tells you what it does, and that's all you need to know if you're placing a bet at the racetrack. Two totally different, yet equally valid, ways of describing the exact same thing.
And this really leaves us with a powerful final thought. This core engineering principle, choosing the right level of abstraction for the problem at hand, it isn't just about transformers. It's about knowing when you have to embrace the messy reality and when a simplified model is actually the smarter choice. So my question to you is, where else in your world do you choose a useful model over the complex truth just to get things done?